Hello everyone, welcome to this new video. In this video, we are going to be building a RAG-based functionality from scratch without using any external libraries like Langchain or any such external libraries. So I won't be writing any code in this video because writing code will take some time and I have already written most of the stuff. I just would be walking through these codes and explaining the relevant concepts as and when it is required. Okay, so let me first of all quickly talk about what exactly are we trying to do in this video. So we will be so in this particular section, what I want to do is I want to start talking about the theory of RAG, and this will basically prepare us for the further sections where we will be looking at the code to implement this RAG functionality. And if you really look at this particular concept, it's very intuitive, it's not very difficult to understand. So we just need to understand the individual pieces. Okay, so let's try to unwrap this whole RAG thing and try to understand it one by one. So usually when you go to ChatGPT and you enter your question, what happens is ChatGPT is basically trained on a data which is limited in time frame. So it's limited up to a certain time, and it will only be able to give you answers based on that. But it has become really good in responding in a natural language, right? That's where you can think of ChatGPT or in general LLM as a brain. Okay, now if we talk about the LLMs will be used in the third stage, the generation part. Retrieval is something uh, where we are going to retrieve some of the relevant documents from our knowledge base. So okay, so essentially we will have a query. This will be a user query. Suppose user asks a question about employees or maybe about HR policies. So employees might ask questions related to HR policies. Now LLMs like ChatGPT, Gemini by default are not trained on a given company's HR policy because those are private to the company, right? uh, LLMs are trained on a open data, right? So what we do is we build a system of retrieval. So we take the query and we do some sort of embedding. So what we do is we try to convert this query into a vector, and we also have a in the background a index. Now what is an index? Let me write it down. So index is basically, you can think of index as collection of uh, vector embeddings or vectors, vector embeddings, I would say would be a better word. Collection of vector embeddings of the knowledge base. Okay, so what I do is I take my query, I convert it into a vector, and I compare it with all the vectors which are in my index, and I return the most relevant ones. And what I am trying to return here, so first I will return most relevant vectors, and from there I can return those sections from the HR documents which are related to these vectors. Okay, so essentially in the retrieval stage, what will happen is, so retrieval stage will give me documents, so supporting documents, I'll say supporting documents. Now what will I do with these documents? I'll augment the prompt. And which prompt? The prompt that I'm giving to LLM. So what I'll do is I will write a prompt like this. Something like, so I'll design my prompt where I'll say answer the user query, and I will write the entire user query based on these documents. And which documents I'm talking about? The document that I generated from the sorry, not generated but retrieved from the retrieval step. Okay, so this is the beautiful concept. So what we do is we do retrieval stage. In the retrieval stage, based on the embedding similarities of the internal document similarity, we retrieve top documents, we augment our prompt using those documents, and we generate it finally. So we create a prompt, and inside that prompt we write the query and documents that we have retrieved, and we simply pass those pass that enhanced prompt to the generation model, which is usually an LLM, and LLM hopefully answers the user's query based on the document that we provide. So this is the basic architecture of the RAG, the way it works. So we will be trying to implement this RAG functionality, and one of the most important stages of the RAG is this retrieval stage. Now, what is the retrieval stage all about? So in the retrieval stage, so meanwhile while I'm talking, let me connect and let me also upload the data that I would be using. So the data that I am using, let me go inside that Hugging Face Wikipedia. So the data set that I will be using is from coming from this page. One second, let me show. Yeah, so this one, and this Sparkit file is about 130 megabytes, and this data is basically having about 200k articles, simple Wikipedia articles. So I'm trying to build a RAG based functionality on top of that. So let me upload that data really quickly here. So while this is being uploaded, I can talk about this retrieval stage. So yeah, so this retrieval stage, the way it works is, this is basically a stage where we retrieve the document based on a user query. So we have a user query. Okay, so suppose uh, who was the first president of United States. Although this is a very common question, so even ChatGPT knows this question, and usually we implement RAG functionality for those applications where only the LLM alone is not enough. Okay, but just to demonstrate the concepts, let's take a simple question. So now, who was the first president of United States? Now this question um, is what we are interested in, and I have some internal internal documents with me, and this internal documents uh, let's say I have got maybe 50 internal documents. Okay, now I want to take my user query, and I want to take my 50 documents, and I want to embed these. And what do I mean by embedding? Embedding is basically a way to represent my sentences or documents in a vector representation. Okay, in a vector representation. And once I have this vector representation, next what I want to do is I want to compute similarity of each of my query vector. So what I will have is, I will have a query vector, something like this, and I will have a collection of documents vector. So I will have something like a list of lists. Okay, and this first list might be a vector for first document, second list might be a vector of second document, and so on and so forth. Now in the retrieval stage, my job is to take my query vector and compute cosine similarity of that query vector with each of these document vector, and get the vectors, or maybe get the documents which are most similar to the query, right? So once this stage is done, this is the most difficult stage, I would say, because if I am accurate in this stage, later stages are quite simple. The second stage is augmentation. In the augmentation, what I do is I prepare a prompt for the LLM. So I write something like, take this user query. Okay, so I will put the user query here and answer this based on the following documents. And what I do is, in place of documents, I put those documents, those docs which I extracted in the retrieval stage. Finally, after the augmentation stage, next stage would be to generation. So RAG's last letter is generation. So finally, I take this prompt. I just simply send this to any LLM of my choice. Okay. So there are three things that we need to take care of, and I feel most important one is the retrieval stage. So I would want to be as accurate as possible in the retrieval stage. There are a couple of choices that we should have. Okay, we should have to make. In the retrieval stage, we have to get document embeddings and query embeddings. So here we would need to make a choice of which embedding model are we going to use. And there are, let me tell you, there are thousands of embedding models which are available out there, both paid and free, open source. The one that we will be using, sentence transformer, is completely free of cost. It is provided by Hugging Face, and there are got within sentence transformers as well, we have got thousands of open source embedding models. Which one you use, it's up to you. It depends on so many factors. Okay, it just depends on so many factors. What are those factors? One such factor is the storage cost. So for example, if so embeddings, each of the embeddings, vector embeddings, has a dimension. Okay, the one I will be using has got a dimension of 384. But let's say if you use OpenAI's embedding model, the smallest model OpenAI offers has got embedding of dimension 1580 something. Now this is 5 times this one, which means 5 times the storage cost than this one. And why am I talking about storage cost? I'm talking about storage cost because uh, these internal documents that you embed, you will need to store these documents somewhere. Okay, usually uh, people, if we are looking at a enterprise application, they use specialized vector search databases. And one such example of this vector search database is Pinecone. Okay, but in this example, in this video, what we are trying to do is we are trying to use something known as FAISS. This is not a database, but rather a way to do vector search library, to do vector search, and it is created by Facebook AI, or maybe Meta I can write. Okay, so again, coming back to my point, so the in the retrieval stage we need to decide which embedding model we need to use, and that choice depends on many factors, and one such factor is storage cost, how much storage we are ready to take. And also storage is directly depending upon how many embeddings we are creating. Suppose I have got 2 million documents, 2 million HR documents, and let's say let's assume at this point all of these are very short documents, very small documents. In that case, we can create one embedding per document. And if we create one embedding per document, it would mean that each, so we are looking at 2 million, which has got 6 zeros, and then 384, if I'm assuming that I'm going with this smallest embedding, then each entry within this vector would be taking 4 byte. And why it is taking 4 byte? Because usually these are stored in double precision float 32. And if I compute this size, let's try to compute this size, it would be about 1.5 kilobyte. And if you do this math, and I feel what I'll do is 1.5 multiplied by this would be about, I don't know, maybe 3 million. And 3 million, it would be this much MB. and if I do convert it into a GB, so it would take about 3 GB of storage, which is quite huge, and it would scale exponentially as the number of documents increases. Okay, so coming back now, the data that we have got. So I'm assuming my internal document is this data. Now let me run this cell. So meanwhile, this package's installation is complete. So yeah, so my number of documents is this. So I'm looking at 200k wiki articles. So I would be basing my decision for the RAG on these 200k Wikipedia articles. And now if I take these articles, usually these articles are long, and it is not advisable to create one embedding per article. So what we do is we do something known as chunking. And in chunking, what we do is we break each article, break each document or article, whatever you can use, into chunks. So let's say if I break it into five chunks, which means I will have 1 million chunks, and 1 million chunks would mean each chunk for each chunk I will need to create one embedding, right? So let's run this cell, and in this cell what I'm doing is I'm importing some bunch of packages. Now notice here I'm using pyarrow.parquet as pq. Why I am doing this? Because while writing this code, I was trying to write it in such a manner that RAM restriction, so for example, if I share this code with you guys in future, and suppose you are working somewhere in an organization which has got maybe massive data, maybe 20 million or 2 billion uh, documents, then this particular code should work in that situation as well. So what I have done here is I have implemented this function which loads the data in batches. Okay, it does not load the entire data all at once. So this 200k is being loaded in batches. So let's run this cell. So load parquet in batches, and then we have got this function for chunking, and here I'm chunking based on the chunk size. And chunk size, you can think of how many words are there in one chunk. So I've kept it default to 500. And if I run, finally I'm using this model for all mini lm v2, and I'm putting this device is equal to CUDA, and if I run this, it will download the model. Okay, and the model that we are looking at is I guess couple of hundred megabytes. No, only 90 megabyte. Okay, so now finally, after we after this step, I'm defining one function called embed chunks. Now what it does is it takes chunks as a list, and it returns embedding. And how does it compute it? It just calls model.encode, and on top of that chunks, and it does this in a batch size of 64. And further again, as I have mentioned earlier, I'm doing this in such a manner that this can be created and done in a production environment setting. So I'm saving the embedding as well. So in the batches of 10,000. So what this means is it will effectively, it will not create the embeddings for all the documents which are there. In my case, it was a small data, 200k, but I was trying to build this code in such a manner that it can be scaled easily. So let me run this now. Finally, I'm trying to use FAISS library for creating index. Now what are index? Index are just a fancy way of saying that so basically holding all the embeddings together. Okay, so this uses flat L2 based indexing, and this flat L2 indexing is a type of index which does not do any sort of index compression and all. So this you might need to look at maybe for your application, because it is not doing any sort of fancy optimizations. So it is just taking the index, and it is loading the saved embedding, and it is adding that in the index, just that. And finally, and in this step, we are doing most of the training and saving and all. So what it does is it loads parquet in batches, in the batches of 1 lakh, and it takes the current data frame, it loops through the data frame, and it chunks text, and after that it also creates some metadata. Why is metadata required? Because after computing similarity, you would need to know the so for example, if you get that these vectors are top similar vectors, you also need the actual text, actual chunk. Okay, so after this we generate embeddings. We save those embeddings, and we also save metadata. Okay, so now if I run this, couple of logs will be printed, and finally I also save this index, because this index is what will be used to make predictions. Okay, so if I run this, it will start processing batch 1, and the way it works is it will start processing batch 1, it will start and you will also see on your left, you will see couple of okay, so it has started embedding, and it is quite fast because currently I have enabled the GPU, but still it's slow. So what I'll do is I'll let it happen, and I'll pause this video, and I'll resume it once this is done. Okay, so now you can see on your left, we have got embeddings batch 0, 1, 2. And why there are only 3 embeddings? Because there were little over 200k documents, and I am running this job in a batch of 100k, which means there are 3 embedding batches which are saved. Now that this cell has been completed, the only thing that we need is this Wikipedia index. And if you notice the size of this Wikipedia index, this is close to 350 megabyte. This is only what we need now. And the metadata .pkl is the overall metadata, and these are individual batch metadata. We only need metadata file and Wikipedia index file. Finally, in the inference part, and I'm only talking about the inference of retrieval, I'm assuming that the part that we did above the inference part, all of those cells have been executed in some other script, and now within the retrieval we are re-importing all the things. And if I rerun this, it will take some time, and then I'll load the index and I'll load the metadata. So once this load is completed, now what I can do is I can query some maybe let's query United States, or maybe the question that we started with, who was the uh, first president of United States. Okay, so now if I run this, okay, so you see first inauguration of George Washington, we are getting result 1. Now what is this result? This is a chunk, this is not the article, but it is giving you the URL of the article. This whole article is there, but then the embeddings were run on the chunks of text. Now you might be wondering, like, where is this URL coming from? If I go here and if I try to show you and basically print the DF, you see this DF not only contained the text of the Wikipedia but also the URL, and this URL were stored in the metadata during the training. So this is where it is coming from. Now we are done with the retrieval part. In the retrieval stage, we just retrieve the chunks, but currently the answer is not there. We are asking something but no answer is there, and that's where we are implementing RAG. And in RAG, as we discussed, we need some sort of LLM, and for that I'm utilizing OpenAI as the LLM, and I'm getting OpenAI API key, and where I can store. So on the left, if you come, you can see these secrets, and you can store all bunch of secrets. I have stored a variety of secrets, and I have given this notebook the access of OpenAI API key. And if I run this, it will load the API key. And finally, if you see this setup, the main thing that is happening is here. So I'm creating this context, which is basically document title and document chunk text, and I'm providing this context here. So context is there, question is there. So answer in a concise, accurate manner based only on the above context. So let's run this. So after this is run, now we can ask the question. So who was the first president of United States? If I run this, it will take some time because now it is querying the, yeah. So you see, answer, the first president of the United States was George Washington. Top documents used are these. So what we have just done is we have built a simple RAG based system. Similarly, we can ask another question: what happens when we die? And if we run this, we can get the answer based on the article. Now if I try to ask something which is not covered in the document, maybe some random stuff, I don't know, but I can't look at these 200k articles. Maybe what I think is not covered is covered. So let's say, who is Salman Khan? Let's see. Okay, so it is covered. Let me see. Let me try to think of some recent happening. Okay, what is Operation Sindhu? So this operation recently occurred in India. Let's see. Oh, okay. So you see this? Uh, it says the provided context does not include any information about Operation Sindhu. Therefore, I am unable to provide detail. Okay, so I think that would be it for this lecture. I hope you enjoyed. What I'll do is I'll add this notebook within the comment so that you can play with it. Yeah, so thank you so much for watching this video. Consider giving it a thumbs up and also subscribe for more future such contents. Thank you.